We begin calculus proper with the concept of the limit. However, before we define this term and study its properties, I want us to see why we need this concept in the first place. As often happens, ideas are generated in response to some need. Necessity is the mother of invention. At least that's how the saying goes. So why limits? Here is a problem that will lead us to the need for this concept. We have some function, in this case it's minus 1 over x plus 5, and we want to know the gradient of this function where x is equal to 0.5. So at this point right here, the x coordinate of this point is 0.5. One possible solution would be to draw a line tangent to this curve. In other words, we need to draw the corresponding graph, identify the point, and then draw a line tangent. And of course, then we simply measure the gradient of this tangent line. If you look at this carefully, you can do it for yourself, and you should get a gradient of approximately 4. However, what we want to develop is an analytical method, a method that does not require us to draw the graph. We can just do some algebraic manipulation and then get our answer. How we do this is to, instead of finding directly the gradient of this tangent line, we draw a secant line. So a secant line cuts through 2 points on our graph. The advantage of this secant line is that it is now easier to get an expression for the gradient of this secant line. So the secant line is our dotted line here. However, we don't want to actually go and get the actual value from a graph or anything like that. We want to work with pure ideas. So this value here, yb, is actually the value of the function when x has, well, whatever x value we have here. And the y value here is the value of the function evaluated for x equal whatever this value of x is. And so instead of using this expression, this equation here, we use this one. So pause for a while because this might scare you a bit, but there's nothing to be scared of. This point here is the point. The horizontal coordinate is some x and the vertical coordinate is some f of x. Then we go across a certain amount h. Now we could use some other variable. Some books say delta x, some books say a, some books say b. I'm going to use h. So we go across by an amount h, and of course the horizontal component of this point b then is going to be x plus h. So just take your time and look at it. Don't be afraid. What then will be the vertical component of this point? It will be f of whatever this is, and this is x plus h. So notice if this is x, this is f of x. If this is x plus h, this is f of x plus h. We need the change in the y's, so it's f of x plus h minus f of x. And we need the change in the x, which is x plus h minus x, leaving us just h. I made a few changes here to reflect this equation here. This is the point x, f of x, and this is the point x plus h. We come across a certain distance h, and this is the point f of x plus h. The height here then, remember it's the rise over the run, so the rise here then is f of x plus h minus f of x, and the run is x plus h minus x, which is just h. So pause this and try and see it for yourself. It should not be difficult at all. And that gives us then the gradient of this secant line here. Keep in mind that what we want to determine is the gradient of this tangent line. This expression is the gradient of this secant line. How then can we use this expression to determine the gradient of this tangent line? The answer is simple. All we want to do is go decreasing the value of h until it is almost 0. Now, why can't we just make it 0? We can't make it 0 because division by 0 is not allowed. And so this is why we need the concept of the limit, because we want to see what value this expression approaches as h gets very, very, very close to 0 without actually becoming 0. So let me repeat that. This expression will give us the gradient of this tangent line when h gets very, very small and is almost equal to 0. In fact, so close to 0 that no matter what number you think of, it's closer to 0 than that. The term we use is infinitesimally close. So the gradient of this tangent line is going to be equal to the gradient of this secant line as h becomes infinitesimally small. So we see that here. I've made h a little bit smaller, and notice the gradient of this line is getting closer to the gradient of this line. and I make it smaller yet, and the gradient of this line getting closer and closer to the gradient of this line. So as you can imagine, when h is a very small number like 0.00000000001, this dotted line will, for all practical purposes, be right on top of this solid line. What we need now is some notation, some way of saying this. We don't want to always have to write out an entire paragraph saying that we want whatever this approaches as h approaches 0. So the way we say this is with this expression. The gradient of this tangent line is the gradient of the secant line as h approaches 0. More formally, the gradient of this tangent line is the limit of this expression as h approaches 0. And this expression, of course, is the gradient of this secant line. In the next presentations, we'll go into this a lot deeper, but for now, I think we have established why we need this concept of the limit. It's going to allow us to determine the gradient of tangent lines at various points on a graph, and it's going to allow us to be able to do so analytically without even having to draw the graph. Bye for now.